Good afternoon. This slideshow is going to cover analysis of variance, which is a technique for comparing means when you have three or more groups. And we are going to confine ourselves to what is called the omnibus test in a one-way model. The omnibus means that is the test of a general hypothesis that there are differences among the means somewhere. And the one-way model means that there is only one independent factor. So the omnibus test answers the generic question, is variance on a dependent variable attributed to differences in groups, levels, conditions of an independent variable? The dependent variable, or DV, are scores on the outcome that we have measured. Could be memory, could be reaction time, self-efficacy, survey scores, whatever. Should be a continuous variable at the interval or higher level of measurement. And the factor or factors are conditions that have categorical levels or groups. So categorically measured conditions. So for instance, the membership to a various political organization. If you have the same number of subjects at each level of the factor, the design is said to be balanced. So if you are contrasting people with preference for red, blue, and yellow, and you have 15 people in each group, that is a balanced design where the independent factor is color preference, and you may be measuring something, a personality trait, as a dependent variable. We call the group assignment, or the categories that people belong to within the factor, both levels, groups, and conditions. The words are used fairly interchangeably. And we only have one factor in the type of ANOVA, the one-way ANOVA, that will be covered here. So the statistical hypotheses are for the omnibus null hypothesis, that's the general test, is that there are differences in means somewhere. Mean one is equal to, or I'm sorry, no differences in means. Mean one is equal to mean two is equal to all other means up through the jth mean or the last group mean. The omnibus test, our alternative hypothesis, is at least one mean is different from one other. Some mu sub j, some group, is not equal to some other group for some groups. J is a notation for group. We are going to consider for this kind of analysis running an F test, because we're assuming that we have a factor where group membership is contrasted and a dependent variable that is continuous. But there are assumptions for the F test, as there are assumptions for most of our tests. We are assuming that the participants are random samples and that they're independent of one another. No person is measured twice. There are no twins within any group. The populations are normally distributed on the dependent variable. Now, having normal distributions within the sample is a real plus. However, we consider that the F test, much research has shown that the F test is robust to a violation of this assumption if the samples have distributions of the same shape and the population is normal on the variable. And importantly, the variances of the populations are equal. This is the assumption of homogeneity of variance. It is tested in most computing programs, and for the purposes of this demonstration, we are going to take it as given that this assumption is upheld. So what are you actually going to used to test the general hypothesis if you have met the assumptions and you have the appropriate kind of data. You're going to use an F statistic. And an F statistic is a ratio. It's a ratio of variance between to variance within, variance between groups to variances within groups. Like most of our other tests, it is some contrast in the numerator divided by some error estimate. The randomness of belonging to a group, since the groups are assumed to be a random sample taken from the population or taken from the overall sample often, then we consider that the part of them that varies within their group is random and is an estimate of sampling error. So the numerator term is the variance associated with the independent variable, with group membership, plus some component of random chance. It includes the treatment effect, and that's what you hope will be large. The variance within is the variance assumed to be due to random chance. And F is a ratio. Now note where I have MS. MS is an abbreviation used almost primarily in ANOVA models. It means mean squares or it means variance. It is simply another notation for variance. It is very commonly seen, so you need to know what it is, but it means variance. And you want your F statistic to show a large contrast between mean squares between and mean squares within. Effect size is called eta squared. Now there is and are other effect sizes for one-way ANOVA, which are considered to be less biased according to sample size. However, the basic is still eta squared. Eta looks like a small n, kind of. And it is the sums of squares related to contrast between groups divided by the total sum of squares, which is contains all the information in the data set. In the one-factor, one-way ANOVA only, eta squared can be directly interpreted as the percent of variance in the dependent variable accounted for by group membership. So the notation I use, and it's simplified from some other users, but it's a very common notation. So in one-way ANOVA, you only have one factor. We'll call it factor A right here. And X sub ij, as in everything else done, represents a single score. It represents the ith case in the jth factor. So that, for instance, if the first case the ith case in the jth level of the factor. So J represents the number of levels. So the first case in the third level would be X sub 1, 3. X sub 1, 4 means the first case in the fourth level of the factor. So those are your individual score notations. The group means are indicated by with a mean symbol, X bar, and in the subscript, you have which group is referred to. Its generic form is X bar sub J, but you put in, for any individual analysis, X bar sub 3, for instance, which is the group mean for the third level of the factor. And the grand mean is indicated with one dot in the subscript for the mean. Grand mean means the mean score for all cases in the data set, regardless of group membership. the essential calculation components that you need is n sub dot. I probably the only person who uses that notation, but I use it to mean the total n in the sample. The n per group. Okay, the assumption in ANOVA is a balanced design. It's okay to have some variability from a balanced design, not too much. Otherwise, you're jeopardizing the assumption of homogeneity of variances. And the hand calculation is much more difficult. And so anything that I would show people to hand calculate will have equal ends. J is the number of groups. You need to know that. You will need to use the raw data, if you are working from raw data, to calculate the total sums of squares, sum of squared deviations from the mean for all individual cases deviated from the grand mean. That's the total sum of squares within, sum of squares between. And you'll need to know the degrees of freedom for each of your terms. You have the total, and then you have the degrees of freedom within, which is associated with the denominator of the f, and the degrees of freedom between, which is associated with the numerator. So we're going to have an example now and go through all the steps for the null hypothesis, significance testing, and the effect size. So we're looking at the effect of short-term memory, the effect on short-term memory of different temperatures for learning. And we have three groups. One group is engages in learning in a room that is heated to 50 degrees Fahrenheit, another in a room that's heated to 70 degrees Fahrenheit, and the third in a 90-degree room. There are 5 cases within each group. The researcher predicts that there will be a mean difference in short-term memory among groups. There's no hypothesis about specific directions of difference. It's an omnibus hypothesis that there will be some difference. The independent variable is group membership on the temperature factor, and the dependent variable is count of problems solved, and that is a ratio level measurement because there is a true zero, you can solve no problems correctly. So here are our steps. You state the null hypothesis and the alternative hypothesis. Note, in other cases, we've determined whether to use a one-tailed or two-tailed test. We do not do this in the omnibus test, the test of the overall ANOVA. All tests are non-directional. We decide the type of test based on whether or not it meets the characteristics for an independent variable, a dependent variable, and whether assumptions have been met, and what kind of research questions we're asking. Establish the level of significance and use the degrees of freedom to determine the critical value. 4, calculate the test statistic. And 5, make a decision about the null hypothesis. And then after we have finished the null hypothesis significance test, we'll estimate the effect size. For the omnibus test, we do not calculate the confidence interval. So here are our data again. And our first step is to state our hypotheses. The researcher is predicting some mean difference among the groups. So this is a time to pause and sketch out what you would think would be the hypotheses. The hypotheses, one way of stating the hypotheses is just the generic formula. For the null, mu1 is equal to mu2 is equal to all the other mu's up through the last mu. And a way to state the alternative is that there is at least one difference. Now we go on to step 2. Note that at the bottom, I've repeated the hypotheses, but I've simplified the null because we have 3 groups. I've just written mu1 equals mu2 equals mu3. We know exactly how much it groups, so it's fine to write it like that. Now, we have to decide the type of test. Again, we have 3 levels of one categorical factor. You could say that these were ordinal, but ordinal for the independent variable is fine as well. And the dependent variable is continuously measured. So now we have to think about our assumptions. So the assumption we're primarily worried about is the assumption of homogeneity of variance. You can test this in most computing programs, including SPSS. For the purposes of this demonstration, I'm going to state this assumption is met. Therefore, I'm giving that assumptions are met. These are the kind of data the F-test is appropriate. Can you see here, the hypothesis stated that the F-test is appropriate. So now step 3. If you can remember step 3 is establishing the level of significance, the alpha, and the critical statistic. So I am going to say, yes, we're doing the F-test, we met the assumptions. We're all going to say that. The only unique piece of information not otherwise found was that the assumptions have been met. I'm also going to state it as a given that alpha is 0.05. But to find the critical value, we have to use the F table or an F critical calculator online. You use the F table. F tables are available in most textbooks. And the F critical statistics require 2 degrees of freedom. They require a degree of freedom because it's a ratio. Each of the terms in the ratio, the numerator and the denominator, is a mean square. Each mean square or variance has its own degrees of freedom. So you're going to have a degrees of freedom for the numerator term and the denominator term, the between term and the within term. The degrees of freedom for the between term, which will give you the mean squares between for the numerator of the F-test, is j minus 1, where j is the number of groups. The degrees of freedom for the denominator term is the total groups, the total sample size across all groups minus the number of groups, or an alternative way of writing that formula is the number of groups times the number of cases within a group minus 1. The typical way of laying out a table for looking at critical values is that you will have numerator degrees of freedom, between degrees of freedom, arranged in columns. Nu1, 2, 3, 4, and 5 is what you can see here. And denominator degrees of freedom, Nu2, arranged in rows. So degrees of freedom in the denominator of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, where you're going to look is to see where you have the combination of your actual degrees of freedom for the 2 terms to show your critical value. So you can think now, oh, what are my numerator degrees of freedom and what are my denominator? What is Nu1 and 2? And where do they meet? So because we have 3 groups, our j minus 1 is 3 minus 1 is 2. So we're going to look down the 2 column. Because we have 15 people in the total sample minus 3 groups, that's 12. or 3 groups times 5 minus 1, which is 4, which is 12. So our denominator degrees of freedom, our degrees of freedom within, is 12. So the intersection of 2 and 12 is 3.885. And you would write that F212 equals 3.885. So you see there all the information for step 3, steps 1 through 3. Step 4, this is actually calculating the F statistic. So let's get into it. What I have down here is a suggested setup example for running through this problem. It is not the only way of organizing the calculations. If you're calculating by hand, it is the way that I use. The essential terms, or at least some of them, the names for some of the essential terms, I've got in yellow. And I've colored slightly differently all the data for the different groups. And I've left columns to do the hand calculations in. And I've labeled things. So these are kind of things that I feel are necessary to use. Adequate number of columns. I actually could have put in at least one more column for each group, but I didn't for the sake of space. Appropriate labeling. And usually I often will use some kind of color contrast so that I can, if I can, I will find some way to draw attention to the essential terms that I've calculated. So I've put all the raw data in under its specific groups. Group 1, raw data, 0, 1, 3, 1, and 0. Those are the scores from these, and etc. under group 2 and group 3. And it matches the data in the original set. So now you see our formulas. And down at the bottom, what do we need for this test? Well, we need all the individual scores. Got it. Partly done already. So we need all the individual scores. Now we need that grand mean, that X bar dot, okay, the mean of all the data points. So that means the average of 0, 1, 3, 1, 0, 4, 3, 6, 3. You do that any way you want to. You can do it by group. You can do it all in one rush. But you calculate the grand mean. That's not too hard. So there's our grand mean. Grand mean is 2. Circled in green. So what do we need next? We need the group means. The group means are necessary for calculating the sums of squares between, which is our transition point to get to the mean squares between the numerator of the F statistic. You see in that formula, there X bar sub j is each group mean. So again, group means, none of this is hard to calculate. Group mean, group 1, 0 plus 1 plus 3 plus 1 plus 0 divided by number of people in a group, which is 5. So we can go, and you can do this, you can pause, calculate all your group means. Okay, so I got the group means in there, circled in green, and we're good with the group means. Check. So now what we're going to have to do next is the group variances. And the group variances are for the sum of squares within term. Up there, sum of squares sub W is equal to the sum of all the group variances times their respective degrees of freedom. Now, there is actually an alternative formula to this, which we'll see later on. Sometimes one is simpler, sometimes the other is simpler, but regardless of which one you use, you have to have the sums of squares. So the sums of squares, these are the sums of squares within. which means that you're only looking within groups. And I've filled in a couple of the squared terms, squared deviation terms that you're going to use to get the sums of squares for each group. So we're talking about the third column from the left, which is headed deviation within, related to group 1. And that is going to be the scores deviation from its group mean. Sums of squares within groups. So its deviation from its group mean. Its group mean is 1. So its deviation is 0 minus 1. And then, as always, we are going to square the deviations. Once we squared all the deviations, we can proceed to sum them. For group 2, we have I'm sorry, I seem to have left out the notation x bar sub 2, but x bar sub 2 is 4. And so to get the first scores deviation score, it's going to be at scores. Group 2 first case is 4. Minus the group mean is 4, which is going to be 0 squared, and so on. So I invite you, pause, calculate these scores. Oh, thank goodness, my x bar sub 2 has appeared again, and now this reveals all those terms necessary for the sums of squares. The group 1 sums of squares is 6, group 2 sums of squares is also 6, and group 3 sums of squares is 4. So now we have to calculate the variance. Now, again, there is an alternative formula to this where you don't have to calculate the variance. I'm going to use this formula just as a reminder about variances, but and variances are a step toward the standard deviation, and you need those anyway for essential reporting. So you probably are going to calculate variances anytime. So our variances, we know the formula for variances. Variances are sums of squares divided by degrees of freedom. Degrees of freedom, each of these sums of squares is within a group. So degrees of freedom are the group size minus 1. So we're going to take each of these terms, our group sums of squares within components, and divide them by number of cases in a group, minus 1. And that will give us 1.5, 1.5, and 1 for the variances across the groups. So we're still working on sums of squares within. If you look at the formula in the upper right, sums of squares within is the sum of the degrees of freedom for a group times its variance. And we have all the variances. We now have kind of everything that is down there that we need to calculate our mean squares. Or first, our sums of squares, then our mean squares, then our. That's good. So I'm sorry, I was a little bit distracted there for a minute. We're going to start calculating each of our big terms: sums of squares between, sums of squares within, sums of squares total. And we have all the components we need for that. So sums of squares between, n sub j times the sum of all the squared deviations of group means from the grand mean. Okay, what's that about? We take each group mean and deviate it from the grand mean. Square it, that's what's in parentheses. Each group mean deviated from the grand mean. Square that term. Now we have a squared deviation term. Sum all those up. How many will we have? When we have three groups, we'll have three terms to sum. And then multiply that sum times the number of cases in a group. Easy to forget. Multiply the sum times the number of cases in a group. So for instance, for the first group, you're going to take the group mean, which is 1, minus the grand mean, which is 2. 1 minus 2 is -1. You square that, 1. You're going to get that term for each of your three groups, the group deviation from the grand mean. Add them up, and then you multiply by the group size, which in this case is 5. So you're going to have 1 minus 2 squared, 4 minus 2 squared. Group mean for group 2 is 4. Grand mean is always 2. And 1 minus 2 squared. The sum of all of those times 5. And we're going to see a the sum of squares between is 30. Wonderful. We have three major terms: sum of squares total, sum of squares within, and sum of squares between, and we have one of them. The total sums of squares is each individual score in the formula. Look in the formula, the parentheses is x sub ij, every single little x. I shouldn't call it little x here, that's a deviation score. Every single x value minus the grand mean. Each of those squared. Okay, deviate each score from the grand mean. Square those deviations. Add them all up. So I've done the first couple for you. For the first case in group 1, that's x1, 1. The value is 0. The grand mean is 2. So it's 0 minus 2, that's its deviation, squared. 0 minus 2 is -2, squared is 4. So that is that score's squared deviation from the grand mean. Group 2 first score, that's x1 is the first score. Group 2, x1, 2 is a 4. 4 minus the grand mean of 2 is 2. 2 squared is 4. So you're going to do that for every score in the set, and then you're going to add them all up. And I've done it for all of group 1 with resulting data of 4, 1, 1, and 4, and so on for group 2, and so on for group 3. And I have, you could add them all together, or you could add them, in 3 swatches. I've done 3, 4 plus 1 plus 1 plus 4, and then each other one and get 11 plus 26 plus 9. However you do it, my answer is 46. We hope that's right. We hope that's what you get. So now we have sum of squares total and sum of squares between. All you need is sum of squares within. So this is where I show you that there are actually 2 formulas for sum of squares within. If you have the group variances, you can multiply each group variance times its respective degrees of freedom, and then add all those. Now, because we have equal group sizes, the degrees of freedom for each group is 4. Number n minus 1. 5 cases in a group is 5 minus 1 is 4. And then we have each variance. So for instance, you would take the variance for group 1, which is 1.5, shown up in the data screen, and multiply it by 4. And so on. You'd get all of those terms and add them up. An alternative is that you can, the formula looks more complicated, but actually if you have sums of squares, it's easier. It is just summing up all of the sums of squares that you've already calculated. Those are the first terms at the bottom of let's see, the deviation squared within column. So for group 1, that's 6. A little bit hard to follow everything along. It all depends on labeling. So if we take sums of squares within using the first formula, the first term will be degrees of freedom for a group, which is n minus 1, which is 5 minus 1, which is 4, times 1.5, the variance for that group. The second term will be degrees of freedom for the group, 4, times the variance of the second group, which is also 1.5. And so on through the last group. The second formula would be the sum of each within group sum of the squares, which is the squared deviations within. For group 1, the squared deviations with sum of squared deviations within is 6. For group 2, it's 6. For group 4, 3, it's 4. So I've written it out for both versions here. 4 times 1.5. 1.5 is the variance. 4 times 1.5. 1.5 is the variance for group 2. And 4 times 1. 1 is the variance for group 3. The alternative way is sums of squares for group 1, sums of squares within for group 1. That's 6. Sums of squares within for group 2. That's 6. And sums of squares within for group 3. That's 4. So total sums of squares within is the sum of all the group sums of squares within. And either way, I get 16. Doing it both ways is a useful check. Now, your other useful check is that we have calculated sums of squares between, sums of squares total, and sums of squares within now, all 3 of them. And sum of squares total is always supposed to equal the sum of between and within. So we can look here. Does our sum of squares between plus our sum of squares within equal our sum of squares total? If it does not, we have a mistake. So, does it? Yes, thank goodness. Okay, so now we can proceed, having all of our sums of squares, to the much quicker phases of this, where we get the mean squares from the sums of squares and degrees of freedom, and then the overall F. We're still on step 4, calculating the test statistic. So, our F ratios, mean squares between over mean squares within. What are our mean squares? Our mean squares are sums of squares divided by their respective degrees of freedom. We went to all that trouble to get our sums of squares. It's really just the trouble of getting sums of squares when there's one or two groups multiplied by the fact that you have multiple groups. So mean squares between, sum of squares between over degrees of freedom between. These are the formulas on the lower right. Sum of squares between, we calculated. It's over there in pink. Degrees of freedom between is the number of groups minus 1. J minus 1. Mean squares within, sum of squares within, which we calculated and checked, over degrees of freedom within, which is overall sample size minus number of groups, or number of groups times the quantity group membership minus 1. So you can think through, what are all those terms? Calculate it out. And those will give you the mean squares between and the mean squares within, the terms you need to finish the F ratio. Okay, so we have our mean squares between. Sum of squares between is 30. Mean squares, or degrees of freedom between is J minus 1 equals 2. Mean squares within, sum of squares within is 16. Degrees of freedom within is 3 groups times group size of 4 is 12, or overall sample size of 15 minus 3 groups is 12. And our obtained F, the end of step 4, is the ratio between those two things. 11.25, 11.28, one has more rounding error than the other. Your answer should be in that range. Okay, congratulations on the F. What is step 5? Step 5 is the decision. So the hypothesis, testing the actual test. You've set up the hypothesis. You've identified your critical statistic. Remember what it was? It was 3.885. You have your mean squares terms, just what was in the previous slide, 15 and 1.33. And you calculated your obtained statistic, approximately 11.25. And now you have to make a decision. You compare your obtained F to your critical value. If the obtained F is greater than the critical value, you reject the null hypothesis. If it's less than or equal to the critical value, you retain the null hypothesis. Your decision in this case, reject the null hypothesis. Hooray! The null hypothesis significance test is done, and you successfully rejected it. At least one mean for memory on multiplication facts, is what I recall, is different from one other when group room temperature was varied. Now we do our last step for the one-way overall ANOVA, which is the eta squared, the effect size. And that is very simple to do once you've done all this work, because it's your sum of squares between divided by your sums of squares total, the ratio of 30 to 46. And it can be uniquely interpreted as, only in the case of the one-way ANOVA, as the percent of variability in the total data set attributable to group membership, or in this case, attributable to room temperature. So 30 divided by 46 is 0.65. And in terms of size, that's a large effect. So altogether, we have our hypotheses. Null is all groups are equal. mu1 equals mu2 equals mu3. And alternative is at least one mu is different from another. Our critical statistic, our obtained F. Our decision is to reject the null. At least one mean is different from one other. And our eta squared is 0.65. If we want to put that into an APA write-up, we're going to say something like 15 children were randomly assigned to 3 groups for instruction, with 5 children per group. The first group was placed in a cold room set at 50 degrees Fahrenheit. The second group was placed in a moderate room, 70 degrees, and the third in a hot room, 90 degrees. All were taught multiplication facts for a 15-minute session and then tested on recall. One way ANOVA was conducted to test the hypothesis that there's a difference in children's math memory related to the room temperature for learning at alpha equals 0.05. The assumption of homogeneity of variances was upheld. Group mean differences in math fact memory in the cold room, mean equals 1. There probably should be decimal places there. SD equals 1.22. Moderate temperature room, mean equals 4, SD equals 1.22, and the hot room, M equals 1, SD equals 1.00, were statistically significant. F11 equals 11.85, DF equals 2, 12, P is less than 0.05. This suggests that children's recall of math facts after brief instruction differs according to the temperature in which they learn. The effect size eta squared was 0.65, indicating 65% of variance in children's recall of math facts could be accounted for by whether learning took place in a cold, medium, or hot room. And that's it for the omnibus test of the one-way ANOVA.